So I want to start from classical systems. And I want to briefly introduce Hamiltonian dynamics. So we normally define them through a set of canonical variables, Qj and Pi, which form a Poisson bracket, which is delta ij, right? And I remind you that a Poisson bracket between any two functions of P and Q is defined. And there are different conventions. I found that I first used convention written in Landau, but then I found it's opposite to most of other books, which at least I found. So I think Landau uses an opposite sign convention, but that's OK. And please let me know if I need to increase my font, I will. But then, of course, less stuff will enter them. So, and then very important concept in classical physics, and it will be central to everything I'm going to discuss in this lecture, is the concept of canonical transformations. So these are transformations which keep Poisson bracket invariant. And as an example, let's take a orthogonal transformation where Q as a vector becomes some orthogonal matrix times Q, or maybe I can put Q tilde just to distinguish. And then P tilde will be an orthogonal matrix times P, right? And we can just explicitly verify that canonical Poisson bracket is preserved under this transformation, right? So I can write Q tilde j will be rjk times qk, and P tilde, say I, will be ril times pl. So if we compute now a Poisson bracket between qj and pi tilde, we will get rjk times rik, right? I should get RIL, but then I got Poisson bracket of QK and PL, and this will give me Kronecker delta. And then I can write it as R transpose Kj, and R times R transpose is 1. It's a Kronecker delta. So, and most of you heard that we can generate canonical transformation through the generating function, but it's a complicated object. So generating function is similar to, as I will discuss, to Unitary, which Eugene introduced. And normally, it's really hard to find. So instead, I want to generate infinitesimal canonical transformation. So that's much easier. So I will be asking, can I define some continuous set of canonical variables? So I'll call them Q, J, of some parameter lambda, so it's some continuous parameter, and Pj of lambda, such that I preserve a Poisson bracket between them. And let me just state without the proof, and then we will check that I can always generate canonical transformation if I say that Qj of lambda plus delta lambda will be equal to Qj of lambda, and I always have to think about signs times dpj, and then pj of lambda plus delta lambda d lambda of q p lambda over d qj, sorry, times delta lambda. And of course, I understand this in the limit delta lambda goes to 0, so I can rewrite this through derivative. So dq by d lambda is minus dA dp, and dp d lambda is dA dq. So you might recognize this is almost like Hamiltonian equations of motion, except for the sign. And that's actually how I remember the sign. So when you do canonical transformation, use opposite sign convention. And we know, I probably even don't need to prove you that this works, because you hopefully know that if we define classical Hamiltonian equations of motion, they automatically preserve Poisson bracket. So Hamiltonian equations can be thought as generator of canonical transformations, and my lambda is time. But here, lambda is arbitrary parameter. It doesn't have to be time. So it's a really simple exercise to check that up to order of lambda, delta lambda, if I compute Poisson bracket of Qj and Pi, I will get delta ij plus delta lambda, and I will get d2a dpj dqi minus d2a dpj dqi plus of the order, something of the order of delta lambda squared, but when we send delta lambda to 0, it disappears. And this gives me 0. So you can sort of see where it comes from, and you can fill in details yourself. So when I expand Q, I will get either correction to Q of the order of delta lambda or correction to P. And Q I have to differentiate with respect to correction to Q with respect to Q. But here, correction to Q is derivative with respect to P. And when I write Poisson bracket in P, I will get derivative with respect to P. And here I have derivative with respect to Q. And they have opposite signs, so they cancel. So if you are interested in this lecture notes, there is a relation between this object, which I'm going to call gauge potential, because this is how it's called in quantum mechanical language. But in mathematical language, it's known as connection. So for those who know math, this is just the connection. So let me give you a couple of examples how it works. So let me consider a very simple canonical transformation. Say I take one coordinate. Well, let me just even give you an illustration. So we have, some car, and we have a particle in the car. And then it's convenient to go to a moving frame. I'll define, say, position of the car as x0. This plays the role of my lambda. Lambda is arbitrary parameter, so here I call it x0 because it has more transparent physical meaning. And I will call this q of x0. And obviously, and this I will call q0. Sorry. So q0 will be my lab coordinate, and q of x0 will be moving frame coordinate. So just from the picture, we just see that q of x0 is equal to q0 minus x0. And because we are dealing here with non-relativistic transformations, p of x0 is just p0. So let's just try to find what is the generator of this canonical transformation. Well, before I plug it in, so generator is A. What is my gauge potential? For translations. Oh, sorry. Sorry for my handwriting. This is A. It's my attempt to write A. A sub lambda.
So A is just equal to P, no?
Yeah, exactly. So generator, well, we know it from quantum mechanics. So one of the reasons I'm telling you this story that we don't really need quantum mechanics for many of the things we learn in quantum mechanics for the first time. So generator of translations is momentum. It has nothing to do with quantum mechanics. Let's just see that it works. Well, it's function which does not depend on x0. It can in principle. So let's just see that it works. So dq by dx0 is obviously -1, right? But on the other hand, it has to be equal to dA dp. And this is also -1. If I write dp by dx0, I will get 0. And it should be dA dq, which is also 0. So I see that momentum is indeed a generator of translations in space. Let me try another canonical transformation. And as you guess, it could be rotations. Where's the eraser? So now I define my coordinates as function of some rotation angle. So q theta will be qx. Suppose I consider two-dimensional rotations. Again, you can check that it's true in all dimensions. Qx naught. Sure, I never remember signs. I think it's minus, right? Minus, well, it depends how you define rotation. Minus sine theta, qy of theta is equal to qy naught cosine theta plus qx naught sine theta. And same for p. So this is an example of orthogonal transformation, which I mentioned before. Px naught cosine theta minus py naught sine theta, and so on. I guess you can already guess what should be generator of rotations. So now my canonical transformations are rotations. So it should be angular momentum along z direction, right? That's as we know in quantum mechanics. Let's just check that it works. So I'll write only one of them, only one of the equations. So dqx d theta, let's see what it is. Let me differentiate in my head and then write the answer. So when I differentiate this, I will get qx minus qx naught sine theta, and here I'll get minus qy naught cosine theta. But this is nothing but minus qy, right? So this is minus qy. But on the other hand, it has to be a minus dA dpx, right? So what I want to say that A will be, I guess, qy times px minus py times qx. So you can immediately see that this works, right? And then you can guess, because it's symmetric between p and q, you can check like all other equations work. So, and I apologize if I mess up signs somewhere, just you can fix it. When we were writing review, we spent a lot of time fixing signs, but it's easy to forget those. So later I will show you less trivial generators of canonical transformations, but at least you see how it works. So any canonical transformation you can really define in this way. So if you can take any generating function which you like and find canonical transformations. Good. So what I told you already, and let me repeat it again, so you can think about Hamiltonian as a gauge potential with respect to time with a minus sign. So it's not going to be necessary, but I think it's very useful. So let me actually introduce second quantization now, because second quantization has nothing to do with quantum mechanics. So normally you learn it through field theory, at least in most textbooks. And I think it's a bit unfortunate. So, and actually, sort of, Eugene already introduced it in his talk in a quantum context. Let me now introduce it in a classical context. And then I will extend canonical transformations to wave picture. So let's say, suppose we have some harmonic oscillator. And in order to define canonical variables, I don't really need harmonic oscillator. It's not motivated. It's like how we do in quantum mechanics, right? We start from harmonic oscillator, introduce creation annihilation operators, but then go beyond harmonic models and still use these operators. So we'll write p squared over 2m plus m omega k squared xk squared over 2. And then I can define, because these new variables. There is no h bar here. I just introduce new nice variables. which I call, for obvious reasons, A and A star. And I can invert it. A k star will be 1 over square root of 2. So I introduced just another. I have two independent variables, Q and P. I introduced A and A star. And that's exactly how it's done in quantum mechanics. And now I can, the question, can compute a Poisson bracket between them. Why not? Sorry, is there a mistake? Oh, QK, sorry, yeah, QK. Yeah.
I mean, there is no I.
Oh, there is no I here, you're right. Yeah, it's Hermitian, you're right. So now I can compute what's the Poisson bracket between, say, AK and AK star. And again, I can do it in my head. So when I compute AK and AK star, I will get minus I times Poisson bracket of Q and P. And then plus I times Poisson bracket of P and Q. These factors will cancel. I will get 1/2. Yeah, I think that's easier. But I will get 2 of them, so 1/2 will also cancel. And I will get minus I. And now you can, of course, do it for various modes. And then you can find that in general, AK and AQ star will be minus I times delta KQ. Moreover, it's convenient to introduce coherent state Poisson brackets. It's coherent states, again, because if you take quantum limit, these are creation annihilation operators, which are related to coherent states. It's sum over K, dA, dAk, dB, dAk star. That's just a formal definition. Minus dA, dAk star, dB, dAk. And if I compute coherent state bracket between AK and AQ star, I'll obviously get 1. So you don't need to define it, but essentially coherent state bracket is equal to minus I times normal Poisson bracket. So now what I'm going to say, without a proof, but it's very easy to check, that these brackets are preserved under unitary transformations. Again, there is no quantum mechanics. I can do any unitary rotation in a star basis, and this will preserve this coherent state Poisson bracket. Moreover, I can write equations of motion for these operators, AK and AK star, just as usually. dAk dt is equal to, again, up to a sign is AK and H. This is just standard Hamiltonian equation of motion for any function which doesn't depend explicitly on time, right? But then I use that this is nothing but I guess there is some minus sign here. No, maybe it's OK. Well, we'll check signs later. So it's minus I times coherent state Poisson bracket, minus I times AK times H. And this is nothing but minus I dH dAk star. Now I can multiply both parts by I. And I get famous Gross-Pitaevskii equation. So many of you probably saw it. So I dAk dt is equal to dH dAk star. And look, I never used the form of H. I used H in the beginning to motivate how I introduce these canonical variables. But this is just definition of new variable. If you want, I'm going to complex coordinates. Instead of classically, I can do it. It's usually not what we do. At least not what we usually do, say, if you go through standard textbooks. But nothing prevents us from going from canonical variables Q and P, going to canonical variables A and A star. And then you recover your equations of motion. So for oscillator, this will reduce. H will be, of course, omega AK star AK if you plug it in. So this derivative will be omega times AK. And then this equation that AK just oscillates in time.
But here this is only about the harmonic oscillator.
No. It's true for any oscillator, any Hamiltonian. So I use harmonic oscillator only to motivate these definitions. Once I introduce this equation is true for any Hamiltonian. Just let me give you an example. And we can even get particle conservation actually from time-dependent perturbation theory, which you also learn in quantum mechanics, and which again has nothing to do with quantum mechanics.
But how do you define A and A star for any Hamiltonian?
It's a complete set of canonical variables. So any Hamiltonian I can express through them, right? It's one-to-one transformation. Now the question, when it's more convenient, and let me just give you an example to motivate it. So let me assume that my Hamiltonian now is P squared over 2m plus m omega squared over 2 Q squared plus some nonlinearity times Q power of 4. And I'm sorry, I'm switching between Q and X because Q sometimes stands for canonical variable, sometimes it's momentum, and I lost track of myself about definition. So Q and X mostly mean the same. So now I can write, let me assume that omega and m are 1, so just to motivate, then Q is nothing but 1 over square root 2 of A plus A star. And then this Hamiltonian will be omega, which is 1 times A star A, plus epsilon over 4. I guess I will get 2 squared, A plus A star to the 4, right? So I'll get this Hamiltonian. This is exact, and these equations, Gross-Pitaevskii equations, are exact for this Hamiltonian. So there are no approximations. But then here we can notice that I will get terms like A power of 4, A star power of 4. I will get something like this. And finally, I will get, is it 4? 4. Sorry, 4. My combinatorics is bad. Say 6A star A squared, right? So, and then they should be cube, right? Did I write square? Yeah, that's why I wrote 3. That's right. So, and then you can write these equations of motion. And then you will see that in the leading order, I will get this dA dt is equal to. So if you write this equation of motion, you might recognize it's exactly what you write when you look into quantum mechanics time-dependent perturbation theory. So this is like your unperturbed energy, because I dA dt will be A, and then plus perturbation. So what you do there, you go to the rotating frame. And that's what Eugene was discussing. And then you convert this to a Floquet problem. And again, because this is not my talk, I really want to mention it. These terms will start oscillating. So if my nonlinearity is weak, these oscillations you can just remove there. Or you can more accurately do 1 over frequency expansion. And the only term which survives is this one. And then you see, well, this really comes from, or this gives you particle conserving Hamiltonian. So just see if you take this nonlinear oscillator with small nonlinearity, then you can convert it to Hamiltonian which preserves number of particles. And then you get your normal Gross-Pitaevskii equations. And you never use Bose-Einstein condensate or anything. So this equation will describe well my nonlinear waves in the limit of small nonlinearity. And then you can even play the game, just numerically compare two approaches, number conserving and number non-conserving. And then you'll see for epsilon with these parameters up to 1, actually, this number conserving approximation works very well. I defined a picture. Of course, it's very interesting to go to fermions. And as we know, there is no classical limit, but that's kind of my weakness because I like it. But if you do something which very similar to what Eugene was discussing, like introduce bilinears, you can even define classical limit for fermions. You can define Poisson brackets and actually describe completely classical dynamics for fermions. And there are many applications when you can describe classically. So one optional exercise which is also discussed in the notes, which you can check, is that Bogolubov transformation is an example of canonical transformation which preserves this Poisson bracket. Again, to define Bogolubov transformation, I don't need quantum mechanics. So remember, Bogolubov looks like gamma k is like cosh theta times a k. I don't remember signs, like minus sinh theta, a minus k star, and same with gamma k star. So if you use this transformation, you can check that it preserves Poisson bracket, and you can even find gauge potential generating function for this transformation. Good. Well, no questions so far. Is it too easy? Well, I hope now it's too easy, because it's going to be harder. OK, so but now I'm going to talk about dynamics. So let me now do a double thing. So let me imagine that I'm solving like a problem when I sit on a merry-go-round. Of course, this is a classic example which is discussed, but just to give you an idea. So suppose I'm going to a moving frame defined through some canonical transformation, where this parameter lambda is itself a function of time. So like for example, when we had a car, this car can move. And then I want to solve this problem. I'm playing ping pong inside this moving car. And car can accelerate. I'm not restricting it. And of course, you can do everything in a lap frame. But then you have to deal with time-dependent boundary conditions. In general, it's difficult. So it's much easier, as we know, to write the problem in a moving frame and forget about dynamics. But then we get extra terms, right, in the Hamiltonian. And you know there are these forces like centrifugal force or inertial force and so on. They all should come from transformation. So let me just put this in a more general ground. So instead of discussing separately rotations and translations, I will discuss general canonical transformations. So I have some set of canonical variables. So far, this is a normal, if you want Q naught, P naught, which satisfy my Hamiltonian equations. I'll go back to Q and P. Everything what I say translates to A and A star. So you just basis choice if you want. So we have dq naught dt is equal to Q naught and H, right? Which is dH dp naught. But now I want to write my equations for Q, which depends on lambda of t and t. And here we're already going to these hydrodynamic derivatives, which are always confusing. At least it takes me always a long time to figure out what is the right sign and so on. So here I just want to highlight so what these two indices mean. So first means that my definition of what I mean by Q depends on lambda, which depends on time. At different moments of time, by Q I mean a different object. Like we are sitting on a rotating frame, right? At time equal to 0, by Qx, I mean something which points at x direction. But at time equal to pi over 2 in units of frequency, by Qx I actually mean something which points along y. So my definition of canonical variable changes in time through lambda. But on top of that, I have a motion. I'm playing ping pong on the merry-go-round. So, and this defines how this canonical variable in a moving frame depends on time. And I want to find what's the equations of motion are. Now, let me do this chain rule. And I'll take a vote. OK. So for which of these objects, full derivative or partial derivative, I am allowed to use this equation? Any guesses? So which is a moving frame derivative, which is a lap derivative? It's all written on the blackboard, but it takes time to digest. It's just meaning of these derivatives, like partial or whatever, is always tricky. You have to really understand what is kept. And that's important, because if you mess it up, you'll get everything wrong. Signs are important. So obviously, I want to say that one is a moving derivative. So it defines dynamics in a moving frame. And one is the lap derivative. So it defines dynamics in a lap frame. And for lap frame, I can use this equation. First time I got it wrong, so don't worry if you make mistake.
Okay, partial derivative must be inertial force.
So it's lab.
Yeah.
Yeah, that's correct. So because think about what this partial derivative means. It means we fix lambda. So we fix definition of our variable and ask how it changes at time at fixed lambda. But that's exactly what Q naught is doing. So we don't change our variables. This partial derivative means that my lambda is constant. It's very tempting to say that this is lap derivative, but then you'll get everything wrong. Right. So now once we figured out with Alexei help, though I asked students, to be honest. So, so we can now use these Hamiltonian equations of motion, right? So I can say that this is dH dP. And then I will get plus lambda dot. And for dq d lambda, I remember there is an opposite convention. So I should change plus to minus and use minus dA dP. Right? And if I do now in this exactly same way dP dt, I will get minus dH dq plus lambda dot dA dq. Right? Again, I will get opposite sign because of my convention. H is like minus gauge potential. And then I see that, well, in my moving frame, I still get Hamiltonian equations of motion. But I have a moving Hamiltonian, which is H minus lambda dot A. And now this should really look familiar to you, right? Because remember, for translations, A was momentum. And then you probably recall that this is a famous Galilean transformation. When you go to a moving frame, H goes to H minus Vp. If I do rotations, it's actually a famous transformation to the rotating frame. I get H minus omega. My lambda is theta. It's rotation angle. Minus omega times angular momentum. Let me do one example, which is probably a bit less trivial. Dilations. So, and just again to highlight, what's the merit of this? We're actually simplifying problem a lot if we know what A is. And we, of course, explore it in many contexts. And I'll try to explore it in sort of a general context of quantum dynamics. So if we have a problem where we have a particle in a box, it's so far classical, so no levels. I have a particle which moves in a box, and the box moves itself with some, I apply some force to it and so on. So we can solve it in this problem. It's sufficiently simple in a lap frame. But then, you know, it's difficult because I need to keep track where the boundary is, right? So when particle catches the boundary, it reflects and so on. But we need to figure out when it catches the boundary, because boundary itself moves according to some time-dependent trajectory. It doesn't have to be constant in time. So what we achieved here, we said that let's forget about this motion. So we go to a moving frame. Now my boundaries don't move. But then I got an extra force in the Hamiltonian. So now let me consider slightly less trivial example, Well, it's still probably a problem which is familiar to many of you, but I want to put it in a context. Let's assume instead of a box, I have a piston, which can move left or right. So, I will call now my lambda will be L of t. It will be length of my box, and I can change it. And I want to do the same. I want to solve how my particle behaves. So there is even famous problem from, I guess, Olympiads, right? The particle moves with constant velocity, ball moves back and forth, and so on. But it doesn't have to move with constant velocity. It can move with arbitrary velocity. And I can ask the same question. OK, so let's try to do the same trick. Now we have to define canonical transformation, which is convenient. And here, an obvious choice will be Q of L will be some Q naught times L over L naught, right? So when my Q is equal to L, sorry, yes, when my Q naught is equal to L naught, my Q will be equal to L, right? So if I'm squeezing the box, my Q always changes between, if L naught is 1, my Q should also change between 0 and 1, right? No, it's probably opposite. No, it's opposite, right? OK, good. So let me just write. It's opposite. I want when my Q naught lap coordinate reaches the end of the boundary, my new variable, moving variable, reaches the end of fixed boundary, right? So Q naught, my lap variable, is squeezed, but my transform variable is not. And then just last word. So then I have to define P of L in this way as P naught times L over L naught. So in this way, I will transfer. I will, of course, have correct Poisson bracket relations. All right. So let's try to
Before
yeah.
starting, can I ask a question?
Sure.
About this famous transformation from PQ to n dagger.
Yeah.
You still have omega letter in that transformation.
Yes.
If you don't have a harmonic oscillator, this omega can be anything.
Oh, sure.
I understand that in quantum mechanics this is just choice of basis, of basis set. Is there some deep analogy in classical mechanics? What's the meaning of
I would say no, you can use any omega, but it's convenient. So for example, if you are close to, you have weak nonlinearity, it's natural to choose non-interacting omega as a convenient choice of definition of A. Because otherwise, well, then non-interacting part of the Hamiltonian is very simple. If you choose a wrong omega, then even non-interacting part of the Hamiltonian will be complicated. So, but it's really a choice. So I guess I was trying to say that you can choose any A and A star which you like, and your equations will always look the same.
So you
but
don't see direct analogy from quantum mechanical basis for...
No, it's direct analogy. But in quantum case, it's also, what's the choice of A and A dagger?
It's choice of basis.
It's exactly the same here. And I'm going to, it's my last classical example. I'm going to go to quantum mechanics, and we'll see that this is really a choice. All these canonical transformations are equivalent to choosing basis in quantum language.
But if you pick up a wrong omega, your Hamiltonian will not be a number conservative, right?
Yeah, exactly. Yeah, precisely. Yeah, so it's always like in this, and this will be one of main themes that we want to find a good canonical transformations. So in general, it's hard. So in simple problems, of course, we know what to do. And I'm showing simple problems to, I guess, familiarize you with language and with various concepts. So this is, I guess, a little bit less trivial. So maybe some of you know what's going to happen, but let me still go through detail. So sorry, let me just again say this is the right choice of Q and P. Why? Because again, the difficulty is that in my lap frame, Q naught oscillates between 0 and L depends on time. So again, I have to deal with time-dependent boundary conditions, and this is complicated in general. So instead, I define variable Q, which always changes between 0 and L naught, right? When Q becomes equal to L, sorry, Q naught. Q naught is not a constant. It's my lab coordinate. Maybe it's a bad choice of notation. Anyway, when Q naught becomes equal to L, my Q of L becomes equals to L naught. So my boundary is always at L naught. Right, now I do my game. So dq dl should be equal to minus dA dp. And this is equal to minus Q over L, right? If I differentiate Q with respect to L, and by the way, that's, to me, one of the main advantages compared to generating functions. If you remember, you have to keep all Q, new P, and then it's such a headache. So here, you just take derivative with respect to L. It's very easy. And then I see that I will get minus 1 over L squared. 1 over L I absorb back to Q, and I will get minus Q over L. So it's simple, right? And then dp dl will be just P over L with plus sign, right? Derivative with respect to L, I just divide by L. It's the same. And then by inspection, we can check that A is P Q over L. And instead of A, we'll call it D. So some people call it dilation operator, some call dilatation operator. I don't know what's the better choice. And then, for example, in this problem, my H will be P squared over 2M minus PQ over L times, sorry, L dot. Yeah. And again, I now simplify the problem a lot. Well, you can probably recall that we can do standard tricks we use in electromagnetism, so I can write ML dot, I can complete the square just to make it a little bit simpler, over 2M minus M over 2 L dot over L squared times Q squared. And now this really looks like a vector potential. Or in our language, and actually that's what Eugene mentioned in his talk, we can now shift momentum. It's a canonical transformation. Generate of this canonical transformation is obviously will be minus coordinate. Momentum was for coordinate, minus coordinate for momentum. So, and we will get, well, sorry, because it depends on Q, it should be Q squared over 2. Yeah. Sorry, it's not a constant, it's Q. But again, I use dp. I call now this lambda, dp d lambda should be equal to minus dA dq, right? And so we see that, like in electromagnetism, A is essentially plays the role of this F. You remember, you shift vector potential by derivative of some function with respect to Q, and you add derivative with respect to time here. It's really this Galilean term for this. So anyway, A will be this times Q squared over 2. So if you do this transformation, you can forget about this, and then I will get M L dot over L dot times Q squared over 2. So anyway, so you will see that this problem becomes completely equivalent to motion in some parabolic potential, which depends both on velocity and acceleration. And you can even kind of see why it is. So, right, if I squeezing the box to the left, then it's more likely for particle to be on this boundary, more likely to collide, and this is like effective potential which pushes it to the boundary. It's attractive. So.
What boundary condition?
It's fixed. So you see, my Q belongs from 0 to L naught always. So you see, I traded in, so the same idea as before. I traded in between time-dependent boundary conditions and extra terms in the Hamiltonian. So what we find is that instead of solving this problem, complicated problem with time-dependent boundary, I just add extra harmonic potential and forget about moving boundary. So that's where many simplifications come, because with this, what I'm going to discuss, with this we can use ordinary perturbation theory. For example, if I'm moving slowly, we can just recover many things which usually, if you try to solve them in a lab frame, require very elaborate work. And I'll go through one exercise soon, and I'll leave it as an optional.
Can I continue?
Yeah.
It's not obvious while looking at this finite Hamiltonian that if you start from q, say, equal to 0, we will not end up at some time with q which is beyond this interval.
No, no, no. There is a hard boundary. So I have to say, in reality, there is extra potential which looks like this. Okay. So I still have this. Yeah, I was. It's not a harmonic. It's like hard wall. I'm assuming there is infinite barrier. So in reality, you can convince yourself that this transformation is useful. And I'm going to define precisely what useful is. It will be equivalent to adiabatic transformation if I can write a Hamiltonian in this way. Plus 1 over L squared times arbitrary function of Q over L. So infinite barrier satisfies this. If I don't have this form, then I will get complicated. I will still get some complications. So I will get complicated time-dependent potential. But I'll get through this. OK, good. So I think enough for classical systems. And after all, in the talk I announced, I'm going to talk about quantum systems. As we'll see, language is very similar. And in quantum systems, I'm going to slowly migrate to special transformations. And then I'm going to go back to classical systems. It's transformations, unitary transformations, which diagonalize my Hamiltonian. So far in classical systems, I was defining some choice of canonical variables and was justifying it by some physical intuition. But if you want to be general, we want to have some guidance which canonical transformation use. So anyway, let's move it slowly. So in quantum systems, I have states and I have Hamiltonians. So I can, and sorry, I always mess up where is U and where is U dagger. And if I mess up in sign somewhere, I apologize. So it's just very painful. So given some state psi, I can always define some unitary transformation. So far, let me untie it from the Hamiltonian just to set the language. Of psi tilde of lambda is equal to U dagger times psi. So far, psi is some fixed state, and psi tilde is my rotated state. It can be a basis state or some other state, right? And then I can now ask how this new state psi tilde evolves if I change lambda. So far, this psi is just some fixed state. It's a fixed state vector. But U unitary depends on parameter lambda. OK, so I can write equations of motion. And for a while, I'm going to keep h bar, because I want to make connection to classical systems. And later, at some point, I will drop it. Psi, right? Now, what is d lambda U dagger? It's minus U dagger d lambda U dagger. Once you get used to it, you just recognize it immediately. If not, you can just differentiate d lambda U dagger is equal to 0, right? Because it's identity. And then you find that d lambda U times U dagger plus d lambda U dagger times U is equal to 0. Now we can multiply. No, it's opposite. Plus, sorry, U d lambda U dagger is equal to 0. Now you can multiply both parts by U dagger on the right, and then you get this identity on top. It's in some sense very simple, because U dagger is in U inverse. When you differentiate 1 over x, you'll get 1 over x squared derivative of x. But because these are operators, you kind of 1 over x, 1 over x put in front, 1 over x put in the back. Okay, good. So let's do this. And then we'll get minus I h bar u d lambda u dagger, sorry, u dagger d lambda u times u dagger times psi. But this is nothing that psi tilde by definition. So, and this is the same as I h bar d lambda psi tilde. So I again got equation which looks almost like a Hamiltonian equations of motion. So I will call this object as A lambda. I'll put hat to highlight it's an operator, though sometimes I'll be forgetting about hats, with a minus sign. Again, for the same reason as in classical systems, I want to define this object, which I will call gauge potential. I will call it A lambda tilde. I'll remove hats. When I mostly will talk about quantum systems. So this is an operator. And A lambda tilde will be I h bar u dagger d lambda u. It's very easy to check that this is Hermitian operator. So I take Hermitian conjugate. You remember I becomes minus I. This becomes d lambda u dagger goes in front. This becomes u. But when I use this formula which I just erased, differentiating u dagger, I'll get another minus sign, minus times minus plus, and I will get the same object. So it's a Hermitian operator. And now it's a generator of unitary transformations. And you can sort of already see that if I'm consistent, this has to be equivalent to generator of canonical transformations, because it plays the role of the Hamiltonian with respect to lambda. So moreover, if you take some operator, say O, then we know that psi O psi has to be equal to psi tilde O tilde psi tilde, right? So we can see that what I'm doing now is going to Heisenberg picture in the usual way. So O tilde should be u dagger O u. And now if I try to write equations of motion for this operator O tilde, h bar, again, I hope I got signs right. I'm not even trying to reproduce them. So again, you can sort of see where it comes from. I have to differentiate u dagger here. I'll get minus sign. I have to differentiate u here. I'll get plus sign. And then if you play, like multiply by u and u dagger, you will get this. So, and you see that, oh, there is no IH bar because IH bar is absorbed into definition of A. So, and then you see I'm getting, again, up to a sign normal Heisenberg equations, but in the parameter space. So same transformation defines not only evolution of wave function, but of all operators. And because of quantum classical correspondence, we sort of see another evidence that this A should be the same as the A introduced in the context of classical systems. So let me discuss a very simple example, just to see that this is something very familiar to you, and just to make this analogy more concrete. So I'll take a very simple Hamiltonian, H, which is just a particle in a magnetic field, or two-level system in a magnetic field, which I can write as minus h cosine theta sigma z minus h sine theta cosine phi sigma x minus I sine theta sine phi sigma y, which is the same as minus h, and I have cosine theta sine theta. I hope it's minus, but could be plus phi minus cosine theta. Now, so far this applies to any unitary, but as I already said, I will use unitary which diagonalizes my Hamiltonian. And these transformations will be playing a very important role, at least in my talk. So I can choose U, and this is something you can check. Now in Mathematica it should take you probably 1 minute, but even without Mathematica it should be quick. So if I define this unitary, it's cosine theta over 2 sine theta over 2 sine theta over 2 e to the I phi minus cosine theta over 2 minus e to the I phi, then my H tilde, rotated Hamiltonian, U dagger HU, would be just minus H times sigma z. So this is just a rotation which diagonalizes Hamiltonian. And of course, this U, components of U, also define my eigenstate. So this will be ground state. This is excited state. And again, it's very easy to see. So if you consider, for example, matrix element of E is excited, G is ground, E, H, G, it should be equal to E naught, or I should put E tilde, H tilde, G tilde. Right. Well, it should be 0, but for any matrix elements, my matrix elements should not depend on the basis. So this is like what enters physical phenomena and so on. So, but because H tilde is U dagger HU, you just see that we must have that G is equal to U times G tilde. And G tilde is very simple. It's an eigenstate of this. It's like 1, 0. And E tilde will be 0, 1. And then you see if you multiply U by 1, 0, you will get cosine theta sine theta over 2. And this is precisely a ground state. So this is, of course, all known. But for me, it's like a way to remember. I always forget whether rows the eigenstates or columns and so on. If you do the simple trick, you always remember it. OK, so now I can be more specific. And I can see what's the equations of motion for my eigenstates. Right? So now I have parameter which depends on my lambda, which is theta in this case, and I have eigenstate which also depend on theta. So I can write that I h bar d theta E, for example, is the same as I h bar d theta. It's U, right? U times E naught. I can insert U dagger U here. So I will get I h bar d theta U times U dagger times E. And if you were careful, this is almost what I had before, but not quite. I had U dagger d theta U, and now it's d theta U times U dagger. So this object I will call A theta without tilde. And as for all operators, remember I defined O tilde as U dagger OU. So in the same way, I define, and opposite, I define A theta as U A theta tilde times U dagger. And now you can see that this is indeed correct. So if I use my old definition for A tilde when I had U dagger on the left, by multiplying by U on the right, I kill it by multiplying U dagger. So if you want tilde and non-tilde is just a basis choice. So A tilde was an operator in the rotated basis, and A is the same operator in the lab basis. So it takes time to be adjusted, but here I would say that if you use the Feynman rule, just close your eyes and compute, everything will be fine. So if you try to think too much about this, it becomes more complicated. But let me just compute what it is, right? So let me compute A theta. So A theta. I'll get IH bar. Then I have to take derivative of this with respect to theta. I'll get 1/2 minus sine theta over 2 cosine theta over 2 cosine theta over 2 times e to the I phi, and sine theta over 2 times e to the also minus I phi. Okay, minus I phi. Is it minus? Yeah, at least in my notes it's minus. And then I have to multiply it by U dagger, which is cosine theta over 2 sine theta over 2 e to the minus I phi, right? Sine theta over 2, and then minus cosine theta over 2 times e to the plus I phi. So I can do it. Well, for example, first row times first column is 0, minus sine cosine plus cosine sine is 0. Here I will get minus sine squared over 2. Yeah, there is something. Yeah, I think both of them are plus I phi. I apologize. I think it's a typo in my notes. Anyway, everything we should come out right. So I will get minus sine squared times e to the minus I phi minus cosine squared e to the I phi. So they add 2, 1. So I will get I h bar over 2. And then I will get 0 minus e to the minus I phi e to the I phi 0. And in particular, when phi is equal to 0, I'll get I h bar. So I will get h bar over 2 times sigma y. And if I choose phi equals to pi over 2, I will get h bar over 2 sigma x plus minus. But then you see that's exactly what we were expecting, at least from the analogy with classical systems. The generator of rotations is nothing but angular momentum. So if I'm rotating in xz plane, at phi equals to 0, it means I'm rotating in xz plane, right? Generator of these rotations is sigma y. So now you can guess, and this I leave as another exercise, that if you compute a phi, then you'll get h bar over 2 times sigma z. So we get what we expect, that these gauge potentials are just generators of these unitary transformations. And now let me go to dynamics.
It's just change of frame.
Yeah, exactly. It's just change of frame. But you see, quantum computation as a process is a change of frame. So we can say that if we can do easily change of frame, we have a universal quantum computer. So I'm kind of slowly going in that direction. So just, you know, is a difficult word. So now, let me assume that I want to solve this problem. So far, it's still two-level system, but of course, I want to go beyond, where again, my Hamiltonian depends on time. Like before, in classical systems, it was the same. It was depending through boundary. Here, you have a magnetic field which can rotate. Obviously, magnitude of rotating of magnetic field doesn't play a big role, just some rescaling of energies in this case. But rotations do play a role. So in some, and let me just even simplify. I set phi equals to 0. It's just to make example a bit simpler. So I have minus h, and then I have as a matrix cosine theta of t, sine theta of t, minus sine theta of t, minus cosine, sorry, plus sine, minus cosine theta of t. So, and you know that in general, it's difficult. So there are various approximations. When theta changes fast, we can go to this Floquet formalism, which Eugene mentioned, and Dima probably will mention. But mostly, I will be interested in situations when h is slow, close to the adiabatic limit. I will go later to situations when h changes fast. And then there will be interesting implications of this. So, and we need to solve our Schrodinger equation. IH bar dt psi is equal to h times psi. So in principle, this is 2x2 system. We can do it in lab frame. We'll get some time-dependent equation and so on. But once it gets more complicated, it's really hard. It's not a setup where we can apply our standard perturbation theory, because we perturb around what? Our Hamiltonian depends on time. Our state depends on time. And here, this moving frame transformation really helps. So instead of psi, I use psi tilde. Yeah, psi is u times psi tilde. OK? So I plug this in. And now it's even easier than in classical mechanics. So I have to differentiate u times psi tilde. And now it's easier in a sense I don't even need to think which is partial derivative, which is full. I now have general time-dependent problems. So my psi depends on time. But now I have time-dependent unitary transformation because u depends on theta, which depends on time. But now it's easy. I just use a chain rule. So I will say that I'll get theta dot d theta u times psi tilde, right, plus I h bar u dt psi tilde is equal to h times u times psi tilde, right? So this is just my time-dependent Schrodinger equation. And now I want to do the same trick as before. I obviously want to multiply by u dagger. Just this term looks like time derivative. So I'll get I h bar dt psi tilde. And now if we look into this term, this will be my a tilde. I h bar u dagger u. And I want to move it to the right. And what we will find is h tilde minus theta dot times a theta tilde times psi tilde, right? It's clear, right? I got h tilde because I multiplied on u dagger hu. It's a rotated Hamiltonian. And you see, even though I used this example, it's completely general, right? I never use specific. When I was deriving this, the only piece of information I need is that u dagger d theta u is my a with I h bar. But this is my definition. So I see that now I got this transformation to a moving frame in quantum mechanical language. And it looks exactly the same as in classical language. And now we can see why this special transformation which diagonalizes Hamiltonian is important. Because if I ignore this term, suppose theta dot is small, then I have no dynamics whatsoever. Because h tilde is diagonal. Like in this rotating, it's just tau z. In principle, in more general, so levels can move up and down. So it means that my phases, if I have phases, I can get some dephasing. I can have phase dynamics. But I cannot possibly have any transitions between levels. It's a diagonal matrix. So this is precisely an adiabatic theorem. So I derived you. And of course, my goal will be to go beyond the adiabatic theorem. Because now, you see, I can use ordinary machinery, which we learn, to study non-adiabatic effects. Because right now, I got essentially static Hamiltonian plus a perturbation if I'm close to adiabatic limit. And we will play with it a little bit, and we'll recover. Hopefully, I'll show like all these things from Coriolis forces Hall effect and mass inertia and so on. This all simply comes from this transformation. So, but this is useful even if we are not very slow. Yeah.
But in this particular case, everything is simplified because you know a tilde.
Yeah. So tomorrow I will mostly be talking how to find approximate A tilde. And I'm going to discuss, indeed, connections of this with integrability and so on. This is related to many, many areas of physics which really go beyond just dynamics close to adiabatic limit. So I don't know how much I will be able to cover, but your question is precisely right. So for complex systems, this object just doesn't exist as a local operator and so on. But this does not mean that there is no approximate complex. In some sense, this A, you can view this A as a generator of these Polaronic transformations, which Eugene was discussing. So now the question, how you find not exact transformation, which diagonalizes Hamiltonian, it's impossible with interactions, but a good transformation, which almost diagonalizes it. And then you can still use perturbation and so on. Yeah. OK. So let me just also say how we can think about this in a lab. About this equation if we use not rotated, basically without tildes. Yeah. And it's completely equivalent, but it probably helps with intuition. So I can normally, when I'm solving equation, Schrödinger equation, right, I'm expanding my wave function in some basis. But now let me expand it in time-dependent basis. So what I'm saying is exactly what's written here, but in slightly different way. So, and now, again, we see why I get sort of non-trivial time dependence. My coefficients depend on time, because I have a generally time-dependent problem. But also my basis vectors depend on time. So I get double time dependence. Now, I write my Schrödinger equation, I dt psi. I now don't use any tildes. I do everything in the lab frame, but with a time-dependent basis. Is equal to h times psi. So now what is this? I h bar sum over a n dot times phi n plus I h bar sum over n a n. Now I use chain rule, and then I will get d by d lambda of phi n is equal to sum over a n times e n of lambda times phi n. Right? That's exact Schrödinger equation. So you see, it's kind of trade in. My left-hand side got more complicated. I got two terms. But my right-hand side is very simple, because h acting on my basis state is just energy. But now remember that I h bar d lambda phi n was a without tilde acting on phi n. And now I see, OK, I can now view this lambda dot as a as a correction to the Hamiltonian. So I can say my moving Hamiltonian now without tildes is simply h minus lambda dot a lambda. And now we see what's the meaning. So here I can write my Schrödinger equation. So this Schrödinger equation I really want to write as a full derivative. So it's real time derivative of the state. And I can write it equivalently as partial derivative, though this is not a conventional notation. Maybe I should put partial moving derivative or whatever, is equal to h moving times psi, where now by partial derivative, I mean that it only acts on these coefficients, not on the basis. Even though the basis depends on time, I ignore it. So this dependence is taken care in additional term in the Hamiltonian. And I only study how my coefficients depend on time. And that's what I want. So these two pictures are completely equivalent. OK. Now let's try to use, how much time do I have still? 5 minutes. It's enough for just one application, just to warm up. I'll derive inertia force for you. So let me do a very simple example. I have a particle in a box. Say box could have some external mass. And now I'm moving my box with some velocity x naught dot. And I want to compute, this can depend on time. I want to compute what's the energy of the box with the particle. I want to use a adiabatic theorem. So I want to do it perturbatively. In general, you can imagine it's a hard problem, because if I start moving box very fast, particle even doesn't have a chance to know what box is doing. I will have very complicated many particle or two particle dynamics here. I make an assumption that my particle moves very fast, in the sense that I have very big level spacing, and I move box gently. And then, of course, everyone should tell me that the correct answer, that the energy should be m plus m times x naught dot squared. But let's see how we can get this answer from quantum mechanics. Try to solve this problem in a lab frame. It's not easy with moving boundary condition, even if you are doing fast. At least I don't know the way how to solve it. But we are going to use moving frame. So we have a Hamiltonian, p squared over 2m plus v of x minus x naught, where x naught depends on time, and v is some potential, say box potential in this case. Now we go to a moving frame, and h moving becomes p squared over 2m plus v of x minus x naught minus x naught dot times p. Now, what's the difference? Well, the difference that now I can treat my basis as time independent. So if you want, I can do this unitary transformation and go to a static box. I can say I'm in a moving box, but I ignore the fact that my basis states depend on time, right? Because when box is here, my basis wave function is here. When box is here, my basis wave function is here. So they have nothing to do with each other. So by adding this term, I'm ignoring this. Now let me go back to adiabatic theorem. So as you pointed, so when x naught dot is equal to 0, this term is 0, and I'm getting basically a static problem. My particle just moves, say, along the ground state or some excited state. But I want to go beyond. And now let me just wave my hands, and I will kind of flash more general derivation and say, actually, to the order of x naught dot squared, we actually adiabatically follow this Hamiltonian. Not static, but this one, to better accuracy. Why? Well, and this is my hand-waving argument, and I will give more rigorous argument later. You can now say, well, this part is basically static. So all dynamics comes from this guy. Now I can do another unitary, which diagonalizes the whole thing. It's known as super adiabatic transformation. So I did adiabatic transformation. You can do super adiabatic transformation. Then you will get another gauge potential. But now this is sort of my lambda. And you will get lambda dot. So you'll get x dot dot. And you'll get, in general, x dot squared. So you'll see that corrections to this guy will be already of the order x dot squared. But in the leading order, I can ignore them. So basically, I can say I adiabatically follow this. I need 2 more minutes, and I'm done. And then I'm wishing to calculate energy. And what is energy? Well, it's just expectation value of static Hamiltonian. This moving Hamiltonian is just a fake object. It's my choice because I decided to solve the problem in some weird basis. But my energy is always expectation value of h. But now I follow the ground state of not h, but this h moving. So this psi is no longer a ground state of h. I can use normal static perturbation theory. I'll say that psi, I can write it psi m naught, psi ground state in the moving Hamiltonian. It's just psi naught. And then minus plus whatever. I don't have time to check signs. Sum over n not equal to 0, my perturbation, x naught dot, sorry, n p 0, en minus e 0 times n, right? So this is ground state of a moving Hamiltonian expressed in terms of eigenstates of non-moving Hamiltonian. And now I plug it in, and I will get sum over n not equal to 0. So x naught dot squared, right? Then I will get n p 0 squared over en minus e 0 power 1. I'll get power 2 from here, right? I will get psi 1 h, psi 0 is 0. because H acting on psi0 is a constant, and psi1 is orthogonal to psi0. So I'll get psi1 H psi1 and psi2 H psi0. Psi1 H psi1 will give me a square of this guy. I'll get energy denominator squared, but because I compute energy, one goes away. I know I'm too fast, but just trust me, I want to finish before chairs kill me. And then you can just check by dimensions. Sorry, I forgot h bar squared because it's part of, no, h bar is contained in p. So p will be h bar times derivative. So I'll get h bar squared from here. I'll get h bar squared from denominators. I'll get 1 over m, which will become m. And I will get dimensionless sum. It's my last equation, which I write. Yeah, it's an interesting sum, so I want to write it. So you will get, if you go through this algebra, you'll get, of course, sorry, E naught. And then you will get sum over n not equal to 1. Well, mx naught dot squared. So all these matrix elements are very easy to compute. This is sine, this is derivative, this is another sine. You will get 128 n squared over 4 n squared minus 1 squared. So you'll get this fancy sum. And of course, you will get E naught plus m x naught dot squared over 2. So you'll get the right answer. But now it really comes from, yeah.
So with the fact that you get just 1/2, seems some kind of magic. Does it depend with the shape of the box?
Yeah, that's, if you want, I derived you a sum rule. So this sum rule really tells you that this has to be equal to mass in Galilean invariant systems. You can verify the sum rule for a square shape. I didn't bother to verify for other shapes, but there is a general proof that you will get m. For any Galilean invariant system, you'll get this. And I will come to that. It's related to equipartition. So, I mean, you'll recover a lot of kind of things which look like magic. But what I want really to say that we see that from this adiabatic perturbation theory, we immediately recover mass as coming from virtual excitations. Virtual because if we send x naught dot to 0, we go back to the ground state, so we don't really dissipate anything here. And we see that it's just because I'm moving the box, I don't really occupy the ground state anymore. You can imagine it. I move the walls of the box, so I'm exciting particle a little bit. And there is extra excitations coming from this population of high excited states. And this correctly gives me the correction to the mass.